So wavelength can be defined in two terms. It can either be the distance between two successive crests, that is this crest, this one, and this one. Then it makes the wavelength. That is, if we're going to consider that, then we're going to do it like this. Consider the distance from the peak of this crest to the distance of the peak of this crest, and that makes the wavelength. That is, our wavelength lambda is this, the distance from this to this, that's the lambda. Then it can also be the distance between two successive troughs, that is the peak of this that is the peak of this trough to the peak of this trough. That is, we are going to show the distance between them. That makes the wavelength as well. So it's defined in two terms, either the distance between two successive crests or the distance between two successive troughs. Okay, the following question is on a paper for May-June 2020. That's paper 4.2. Yeah, that's paper 4.2, May-June 2020. It's saying that Fig 5.1 shows crests of a wave approaching a barrier where the wave is reflected. Then the first question, it says that on Fig 5.1, draw three crests of the reflected wave. So this is the direction of the wave, and these are the crests, and this is the barrier, of course, which is reflecting them. So the most important thing is to make sure that we draw a line which shows, or rather a line which is perpendicular to all these crests, a line which is perpendicular to all of them. So we draw a line here, a dotted line, which is perpendicular to all the crests that we have. And of course, when the dotted line reaches the barrier, then of course we are going to draw a perpendicular line so that we may be able to show the angle of reflection. A perpendicular line so that we'll be able to show the angle of incidence here. Then this is the angle of incidence. Then after that, we are also able to draw the angle of reflection. We know that waves, they are reflected at the same angle that they are incident on, or rather that reflected at the same angle of reflection, which is the angle of reflection is equal to the angle of incidence. So this is the R, which is the angle of reflection. Of course, this is the direction of reflection. So of course, I'm just going to draw the perpendicular lines or the perpendicular crests that go in this direction, which lies in this plane. And of course, I have got another one which is parallel to the first one, all of them being perpendicular to this line, all of them being perpendicular to the direction of reflection. So that's it. The question was asking for 3 crests. So these are the 3 crests. We've got 1, 2, 3. These are the crests. Then item number B, it says that the wave has a wavelength of 36 centimeters and the speed of 1.2. Calculate the frequency of the wave. It's got the wavelength being equals to 36 centimeters, which is equals to 0.36 meters. Then and the speed, which is v, is equals to 1.2 meters. So they're asking for the frequency. So using v is equals to f lambda. Calculating for the frequency, I'm just going to say f is equals to v over lambda, which is equals to 1.2 over 0.36, and this gives me 3.33 hertz, because frequency is measured in hertz. That's it. Then part number C. Hey, this is question number 7 of November 2018, paper 4-1. It says that a laser produces a beam of monochromatic light. State what is meant by monochromatic light. And of course, monochromatic light is a light that has got a single wavelength. Yeah, if a light has got a single wavelength, then it's monochromatic light. Then the part B, the one which requires drawing, it says a wave in air is incident on a glass block. On fig 7.1, or rather the fig 7.1 shows wave fronts at the air glass boundary. The arrow shows the direction of travel of the wave fronts. Then the question comes saying the wave undergoes reflection and refraction at the air glass boundary. On fig 7.1, draw the wave fronts of the reflected wave. So firstly, we want to draw the wave fronts of the reflected wave, and of course it will just go, if I was going to continue with this line, which shows the direction of the wave, and it comes here, of course I was going to have my normal, coming in this direction. Then the reflected wave to be just similar to this one but in the opposite direction, going to the right like this, in this direction. So of course for the reflected wave, I'm going to be having waves going in this direction. It's reflected at the normal, so it will be going in this direction like this. Then I'll be having another one which is parallel, another wave front parallel. Then I've got another wave front parallel. That's what's reflected in the air. Then the question number 2, it says that the wave fronts of the refracted wave, the wave fronts of the refracted wave. So if it was going to be refracted, it was going to go in this direction. They were going to go in this direction, of course, because it's changing direction. They're changing direction, then they will move in this direction. They're going to be refracted, they will move in this direction. They'll move in this direction. From this direction, then they move like this. So in other words, they're going to actually move like this. It's going to have something like this, something like this, something like this, something like this, them going in this direction because they've been refracted away. But I may also want to draw maybe something that links with this. Okay, they're still parallel to this line. They will still move in this direction. They're all refracted like this. That's just still parallel to this one. It's all Okay, this is question number 42 of March 2019. It says that the diagram shows the parallel wavefronts of light. The parallel wavefronts of light wave in eyes. The wavefronts are incident on a boundary. Then the other part is saying the speed of the light wave in air is 3.0 times 10 to the power of 8 meters per second, and the refractive index is 1.3. So the question says that on Fig 8.1, draw the wavefronts of the wave that passes into air. So the wavefronts of the wave that passes into air, one of the most important thing is to make sure that you extend this line of direction up to the boundary. That's to draw a dotted line up to the boundary here. That's the ice and the air boundary. Then to draw the normal, so that may be able to be clear on the angle of incidence. So that's the angle of incidence. Okay, so the angle of incidence. Then now the refracted ray is bigger than the incident ray. It's supposed to be bigger than the incident ray. So it's going to be something like this. Be the dotted line up here. That's the one for the refracted ray. It's coming in this direction. Then of course the the wave fronts will be 90 degrees or will be perpendicular to this line. They're all going to be perpendicular to this line. So we're going like this. That's the refracted ones. That will be like this. Okay, those are the refracted waves, and they're actually supposed to be parallel to each other. So they're all supposed to be parallel to each other. Supposed to be parallel like this. Then the next part of the question, it says that draw the wave fronts of the wave, or rather draw the arrows to show the direction of travel of the refracted ray. The direction of travel of the refracted ray, so it will be in this direction. It's been refracted. Then it says that label the angle of incidence I and the angle of refraction R. This is the angle of incidence, the angle that it makes with the normal, that is I. Then the angle of refraction is this one, R, the one that it makes with the normal down here in the air boundary. Then the next part of the question, it says that calculate the speed of the wave in ice. The speed of the wave in ice. Given the refractive index 1.3 and speed of light. So the refractive index is equals to the speed of light over in air over the speed in glass, or rather here we are using ice. So this will be equals to 3 times 10 to the power of 8 of the speed in ice. That's what we are looking for in ice. Then the refractive index is equals to 1.3. Then if we are going to play with the equation, we'll come out with speed in ice being equals to 3 times 10 to the power of 8 over 1.3, and this gives us 2.3 times 10 to the power of 8. Okay, this is for October, November 2017, paper 4-1, question number 5. It says a wave passes through a gap in a barrier. The wavelength of the wave is the same as the magnitude as the width of the gap in the barrier. Tick one box to indicate what happens to the wave. If the wave is passing through a gap in a barrier, and if the wavelength of the wave is the same as the magnitude as the width of the gap, diffraction occurs. Then all the other options are out. Then the next question, it says Fig 5.1 shows 6 wave fronts of the wave traveling on the surface of deep water with the region okay, I'll repeat. Fig 5.1 shows 6 wave fronts of the wave traveling on the surface of deep water. Incident. The wave is incident on a boundary with the shallow region where it travels more slowly. Okay, then the question says The question says, on Fig 5.1, draw the wavefront of the wave in the shallow water where the wave travels more slowly. Then, of course, the wavefronts are going to be like this because they bend as they go to the shallower water. The wavefronts are going to be like this. This is in the shallow water. And they are supposed to be parallel to each other as well. Then the next question, it says that the depth of the shallow water is now changed so that the speed of the wave in the shallow water is 0.6 meters per second. The speed of the wave in deep water is 0.8 meters per second. In other words, the speed is decreasing from 0.6 meters per second to 0.8 meters per second. Okay. One thing we have to put in mind is that the speed of a wave, when it's moving from the deeper medium to shallower medium, the speed decreases. From the deeper medium to the shallower medium, the speed decreases. And the wavelength as well, it changes. But one thing that remains the same is the frequency. So the frequency in shallow water, frequency in shallow water is equals to the frequency in deep water. Then they've told us that the velocity in shallow water is 0.6 and the velocity in deeper water is 0.8. Then we are going to use the wave equation, which says V is equals to F lambda, or rather the frequency times the wavelength. So making frequency subject of the formula, F will be equal to V over the wavelength. So if F is equals to V over the wavelength, and we are saying that the frequency in shallow water is equals to the frequency in deeper water, then the frequency in shallow water is 0.6 meters per second, which is the velocity, over the wavelength in shallow water. The wavelength in shallow water, that's the one that we are looking for, which is equals to the lambda. Then the frequency in deep water is 0.8 meters per second, and we've been given that the wavelength in deeper water is 1.4 centimeters. Okay, so that's 1.4 centimeters. But one thing we have to know, that we are dealing with meters per second here and meters per second here, meaning that 1.4 we have to convert it to meters, and it becomes 1.4, converting it to meters, centimeters, will be equals to 0.014 meters. So I'm going to have 0.6 meters per second over the wavelength here being equals to 0.8 meters per second over this in meters, because we are dealing with meters, not centimeters. 0.014 meters. Then of course, cross multiplying here, I'm going to end up with 0.6 meters per second times 0.014 being equals to 0.8 lambda, like this. Then of course I divide both sides by 0.8, both sides by 0.8. then the wavelength will be equals to the calculation of this, which will be equals to, that's the wavelength in shallow water will be equals to 1.05 centimeters. It actually comes out as 0.0105 meters, but putting it in centimeters, we are multiplying this figure by 100, so it's 0.0105 times 100. Then this gives us of course the comma moves twice, 1 2, then it becomes 1.05 centimeters.